Let's solve question 8. So in question 8 we still have our function f of x equals to ln of x divided by x, and the domain is that x has to be greater than 0. Now the question is, on which range is our function convex? So what does convex mean? Let's show it on a graph. So let's take an xy axis. Let's take an xy axis, x, y, origin. Let's draw a graph. So let's say it would look something like that. It would look something like that. And how can we explain what is a convex function? Well, let's work through an example. If we take the range of x from 0 until this point, we can see that as x increases, our y value also increases. It goes up. Y takes higher and higher values. How do we prove that the function is increasing? Well, that's from the first derivative. If the first derivative is positive, then the function is increasing. And that's what we see here. The rate of change, delta y over delta x, is positive because we have a positive slope. The function is increasing, is going up. But the question is, how is the function increasing? Is it increasing at an increasing rate or a decreasing rate? And what does that increasing or decreasing rate mean? Or at a decreasing rate? Well, increasing rate, it means that the function increases faster and faster. So as we go from x to higher values of x, our y values increase more and more. So they have an acceleration. And if we look at it on a graph, visually it makes sense, because look how straight up the line is going. The function is literally increasing at a high rate, at a positive rate. Now, to understand this concept better, let's compare this part of the graph with the next part of the graph, so we understand what it means to increase at a decreasing rate. So what if we take the range from here until this point? Again, x takes higher and higher values, so we move along the x-axis. What happens to y? Well, if we look at y on this range, y also goes up, but look how it goes up. It goes up slower and slower. It flattens out. It doesn't have this straight line. It has a more flat line, because the increasing y becomes less and less, and that's what we call in economics diminishing returns. So we do increase the output, we do increase our y values, but we increase it less and less. And the notion of increasing or decreasing rate are proven by the second derivative. So the second derivative has to be positive for a function to have an increasing rate, and the second derivative has to be negative for a function to have a decreasing rate. And the way we call this ranges of an increasing rate or decreasing rate, it's convex and concave. So when the second order derivative is positive, we have a convex range, and when it is negative, we have a concave range. And in our question, we were looking for the convex range, so we need to find out the second order derivative, and let's do it. So we want to find out the second order derivative. Well, what is a second order derivative? That's literally taking the first derivative of x and then differentiating it once again. Remember from the previous question where we calculated the first derivative of our function. It was 1 minus ln of x divided by x squared. So we have to differentiate this once again. We have a division, so that means we're going to use the quotient rule. So let's use it. We would have 1 minus ln of x derivative times x squared minus 1 minus ln of x times x squared derivative divided by x squared to the power of 2. Okay, let's keep solving. What is 1 minus ln of x derivative? One derivative is 0, and ln of x derivative is 1 over x. So 0 minus 1 over x multiplied with x squared. Okay, let's keep going. Minus 1 minus ln of x times, what is x squared derivative? That's just 2x. Divided by x to the power of 2 to the power of 2, that's just x to the power of 4. Alright, let's open the brackets. So we have 0 minus 1 over x, that's just minus 1 over x, multiplied with x squared, and then minus, we have here, okay, minus 1 times 2x, so that's going to be minus 2x, and then minus ln of x, that's positive ln of x times 2x, so plus ln of x times 2x times 2x divided by x to the power of 4. Okay, can we do some simplifications? We can see that we can cancel out an x with an x from here, so we're left with minus x minus 2x plus ln of x times 2x divided by x to the power of 4. Okay, we can see something common here. We can see that we have x in every term. So we have x over here, we have x over here, and x over here. So let's take x as a common factor. What are we left with? In the first term, we're left with minus 1. In the second term, we're left with minus 2. And in the third term, we're left with plus ln of x times 2 divided by x to the power of 4. Okay, what's that equal to? Let's see. Well, that's equal to x times minus 3 plus ln of x times 2 divided by x to the power of 4. And this is our second order derivative. That's what we are looking for. Okay, now remember, if we go back to our function and to our domain, we know that x has to be positive. That's part of the requirement. X has to be positive. How does that apply to our second order derivative? If we look at our second order derivative over here and we know that x is positive, well, let's see. This is already positive. X to the power of 4 is going to be positive because any number to an even power is positive. And we want our second order derivative to be greater than or equal to 0. Well, if these things are already greater than 0, it means we're left with this term over here to be positive. So we want minus 3 plus ln of x times 2 to be positive. Which means, if we do some math over here, we would have, let's take minus 3 to the other side. So we would have 2 times ln of x must be greater than or equal to 3. Which means that ln of x must be greater than or equal to 3 over 2. 3 over 2. How can we get rid of this ln? Well, remember, we can use the logarithmic property where we take e to the power of both sides, because e and ln will cancel out. So if we take e to the power of both sides, we would have that x has to be greater than or equal to e to the power of 3 over 2. And in our domain, we said that x has to be positive. Well, when x is greater than e to the power 3 over 2, x is positive, so our domain is satisfied, which is good. And it means that as a final answer, we would have that the range for which the function is convex is from e to the power 3 over 2 until positive infinity. And we are done.